Cool. All right. So where we were last time is kind of we were talking about how fluid is sequestered in the human body, right? So help me to fill this out. So you're around 60% water because you're a human. And where is the water sequestered? There's two big pools. Intracellular fluid and extracellular fluid. I don't know if you thought about this or looked at which one actually has more by volume, intra or extracellular fluid. There's actually way more intracellular fluid. It's around, if you look at liters, there's around 28 liters of intracellular fluid and only around 14 of extracellular fluid. And of course, what we said last time is that a huge portion of physiology, not all of it, but a huge portion of physiology is making sure that you allow controlled exchange between the fluids and body, right? So you need to get stuff into the cell, for instance, oxygen, yes? And you don't need to get stuff into the cell willy-nilly, pathogens, toxins, right? So you have to have controlled exchange. So they can't be completely separated. And of course, you guys told me last time, what is the physical structure that is the gatekeeper between intracellular and extracellular fluid? Yeah, it's the cell membrane, right? And you've heard selectively permeable 10,000 times since you were in 7th grade, right? But of course, one of our goals with physiology is to figure out what that actually means. Like, how is it selecting? Because it does not have a consciousness, right? So it's selecting based largely on chemical interactions between this mostly lipid membrane and any kind of solute that could be trying to get through. So we do know that. We also know that you need exchange between the two categories of extracellular fluid, which is plasma and interstitial fluid, sometimes also called tissue fluid, right? So why do you need controlled exchange between those? Because if you lose all of your clotting factors out of your plasma, you're hosed, right? So it needs to stay sequestered in your plasma, right? And then your interstitial fluid might need different concentrations of things. But again, they don't need to be completely separated. They need to have controlled exchange between them. Remind me one more time, this is one of the last things that we did last time. What is the physical or anatomical structure that is the gatekeeper between blood plasma and interstitial fluid? What is it? Yeah, it's mostly capillary simple squamous epithelium, right? But let's revisit anatomy. I know you dumped most of it, but you shouldn't have, right? Capillaries are variable in how liberal they are about letting things go, right? Letting things through. Do you remember where in the body is the most limited capillary as far as exchange, the one that protects most from things moving in and out of it? Anybody remember? In the brain? Exactly, the blood-brain barrier, right? The blood-brain barrier, obviously it has to let in glucose and oxygen to the brain, but damn near everything else has to ask permission, and the answer is generally no. But then you also go all the way to the other extreme in which there's capillaries that are holy, not but the other kind of holy, right? Like that, right? Holy. Do you remember? I know I teach my students this. I don't know if everybody does, but do you remember that red bone marrow, for instance, has really holy capillaries, those big sinusoid capillaries? Anybody remember why? Like why you need big freaking holes in the capillaries that permeate through red bone marrow? No, oxygen moves just fine without holes. What are you doing in red bone marrow that might need to go through a freaking hole? Are you making? What's red bone marrow do? Yeah, it makes blood cells. I got a whole blood cell. I need to stick it into the capillary. There's a hole there. Stick it in the hole, right? So it's really, really, so there's capillaries that are in between. But regardless, it's still not willy-nilly, right? You're still going to have some level of protection and control between them. All right, so what we are going to do is we talked about the fluids, right? And we have intracellular fluid and extracellular fluid. A large part of physiology is figuring out, again, what is transported, which a lot of that you've known because you've been paying attention for a little while. It's no big mystery to you that you transport oxygen and carbon dioxide or glucose and waste and other nutrients. Some things will be a little new to you, like why the hell do you spend so much time worrying about sodium concentration gradients? But there are good reasons. They just take a little while to explain. So you've known a lot of the what. You might not be really good yet at figuring out the how it's transported, but you will get good at it because the how is not memorization, it's logic. it's figuring out that glucose is a medium-sized water-soluble molecule, and it can't be transported by this mechanism, and this mechanism, but it can be transported by that one. And then you run into another mid-sized water-soluble molecule, and you say, oh, I got the pattern. I predict that it is going to need a carrier to be transported, right? Does that make sense? So the how you will get, and then a lot of physiology is understanding why. The way that I teach physiology, and I know the way that Joe approaches it too, is don't memorize it. Don't even tell it to me if you don't understand why it's true, right? So really part of the big picture understanding of physiology is not just that oxygen is transported from the extracellular fluid into the intracellular fluid by simple diffusion because it's lipid soluble. That'll be easy for you to get. But what would happen if it wasn't? What would happen if I didn't have an oxygen concentration gradient? What would happen if it didn't get in? So let's back up and just do a little cell biology check. What's oxygen used for inside your cells? Cellular respiration. And if you don't know the answer in physiology, 3 possible answers. Cellular respiration, homeostasis, hypothalamus. Just throw it on the paper. It might be right? So cellular respiration, homeostasis. So that's a lot of what we do with phys. So instead of all of these, one of the reasons I like phys is that you have all these isolated pockets of knowledge. You've got your anatomy knowledge, and you've got your cell biology knowledge, and you've got your chemistry knowledge. For me, physiology, when I truly got an understanding of it, is where they all come together. And it's like, oh, this is why I was supposed to care about pH, because I never did, right? And they kept trying to make me learn cellular respiration all the way into grad school, and I'm like, I'm not going to learn it. But then, physiology, I'm like, oh, it's totally relevant. Okay, so here's a logic question for you. So let me tell you that we spend an awful lot of time and money being ATP, on these fluids in the body, maintaining their composition, their temperature, their pH, their pressure, their whatever the hell, everything, right? We spend so much of our ATP on it that it's actually our biggest energy budget. It's just maintaining the composition, temperature, concentration, whatever of these fluids. We spend 60% of all of our ATP just maintaining homeostasis in those fluids. That means that when you eat a cheeseburger, you don't even have to wiggle and 60% of it is burned, right? I know it doesn't feel that way. You feel like I have to work out forever. It's because you're an American. And in other countries, cheeseburgers are this size. Have you ever eaten in another country? Cheeseburgers are this size, right? And how big are they in America? They're this size. And then the fries that they come with will feed a family of 4 in another country, right? So the 40% that you have to wiggle to burn is on top of what you use just to maintain homeostasis. So it's incredibly energetically expensive to keep everything relatively constant, despite the fact that the external environment is not relatively constant, right? And disorganization is kind of the rule. When I become disorganized as a human, not like as a personality, because that's just true, but when I become disorganized as a human, I'm actually dead, right? So you spend vast majorities of your energy just maintaining homeostasis. But here's a logic question for you. I will tell you that you spend most of that 60% on either the ECF or the ICF, like monitoring the composition, pressure, temperature, pH, whatever, of one of those two. Anybody have any idea which one? Go ahead. Okay, tell me your logic. It's true, it's right, but let's hear the argument too. Oh yeah, that's a fantastic argument. So here's what I have, and there's another reason too. See if you guys can think of the other one when I'm talking. Okay, so here's what I have with ICF. A 150-pound person has around 100 trillion individual pools of ICF, because that's how many cells you have. If you're bigger than me and taller than me, you have more. If you're smaller, you have fewer. But 100 trillion individual pools. They're not all hooked together, right? So my brain cell and my big toe cell do not have a direct communication. So how efficient is it going to be to monitor these all 100 trillion individually for the health of the system? That's going to be outrageously expensive and inefficient, right? Because they're not going to be able to communicate with one another instantaneously. However, What you have as far as extracellular fluid is 1 to 2 pools maximum, right, of extracellular fluid. So I've got my ECF collectively that is subdivided into my plasma and my interstitial fluid. But those two communicate with one another, and they circulate. Yes? Okay. So do you see the increased efficiency of monitoring primarily ECF instead of ICF? Does that make sense? Okay. So it's a big circulating pool. And also what she said, which is that let's say I ingest something toxic. I want you to think about where it goes first. So let's say that I was not a good mycologist and I thought I was eating the fun kind of mushroom and instead I ate the dead kind of mushroom. Right? And fun may be pizza for you. I'm not judging. Whatever. Okay? So I ate the wrong kind of mushroom and it's got a toxin and it actually doesn't affect your neurons, but let's pretend that it does. Let's pretend these are neurons. And I want you to see how many opportunities I have to catch the toxin before it gets to the intracellular fluid. Does that make sense? Okay. So it gets absorbed here, right? What's the first fluid it hits? What's that? That's the interstitial fluid, right? And a lot of times, by the way, because these are fenestrated capillaries, it doesn't even go inside the cells here, necessarily kill those. So it hits the interstitial fluid. I might monitor it and catch it there, right? And then it's going to cross the capillary, and then what fluid is it going to hit? Plasma. I might monitor it and catch it there, right? And then it's going to circulate, right? And then it's going to leave the plasma and go into what fluid again? Interstitial fluid. All of that before it has the possibility of going inside a cell and affecting the cellular function itself. So do you see why it's kind of your first line of defense to monitor the extracellular fluid instead of the intracellular fluid? If, of course, I get it all the way into the intracellular fluid, what's going to happen is if the composition or whatever of the ICF changes very much, the cell function changes. So let's just pretend. I have no idea if this is how it works. But let's just pretend that this causes a massive change in cell pH. Okay? And if it does, it can change the shape of your proteins. Yeah? And when you change the shape of your proteins, you change your enzyme function, and then you change your cell function, right? But you had opportunity to fix it before then. The same thing occurs, by the way, with pathogens, right? You have all kinds of opportunities to actually get a response to a pathogen before it actually infects an individual cell, right? And obviously we're all still alive, so it must work an awful lot of the time. I mean, there's 7 billion people on the planet, so it must work. Okay, so if cell function changes, the organism can become diseased, and then comes the class that often follows this for you guys, which is pathophysiology. Did you take patho?
No.
No? Yeah. Well, you're not like a nursing person, but so pathophysiology is the study of disease function. And most of my students have done really, really well in patho because I don't make you guys memorize. I make you guys build a structure, and then we practice breaking it, right, in class. I'm like, what would happen if that occurred? What would happen if that occurred? And then when you get to patho, you're like, I understand the structure, so it's okay that you broke it here, right? And I get what would happen, and then they just teach you a bunch of drugs that I didn't know, right? Because I don't really deal with living people very often. I deal with cadavers and then systems. And I'm very comfortable because neither one of those ever argue with me, ever. Okay, so physiology, do you think it's all understood at this point? Do we know everything that is to be known about physiology? No, so do you think that there is not just the possibility, but the likelihood that something you learn in here will be modified at some point in the future? Yeah, we're going to learn more about neurotransmitters. We used to think that, for instance, astrocytes had nothing to do with removing neurotransmitters from a synapse. And then somebody 5 years ago says, oh, there's another way of doing that. Does that negate all the information? No, what it does is it just fixes your model a little bit, right? And what I would love is if you guys become medical care professionals. You're one of the kind that I love. And I am a pain in the butt as a patient only if you don't know what the hell you're doing, right? Because if you give me a medication and I say, what does this do? And you're the nurse that says, I don't know, it was prescribed. Like, literally, we've just lost all semblance of trust between us. Like, I ain't doing anything that you want. If, however, you are my OBGYN, that when I was pregnant, my son's 13 now, so it's been a while, but when I was pregnant, I had a high-risk pregnancy because I've got a heart problem. And so we had lots of interactions with each other. And he was both a researcher and an OBGYN. And every time I came in, I would have a question for him, and he would go, oh, okay, I know, like, here's a journal article, and he would email it to me, or I could email him a question, and we would talk about things, and I'm like, all right, Dr. Wild, here, I want to understand why my arms are getting fat. How does this help my baby? And he's like, oh, okay, let me teach you about cortisol. Cortisol wants you to get as chubby as possible just in case things go wrong. I'm like, screw you, cortisol. Why arms, right? You could understand if it was down here, but why exactly do you need this? So it would be fantastic if you were one of those people who did not stop your education when you left school, because those are the best healthcare professionals, the ones that continue to educate themselves. Okay, so let's start talking about, so homeostasis is our goal, and it's going to be kind of our predictor for the entire semester, right? Like if you don't know what to predict, you say, okay, I'm going to look at this and I'm going to say homeostasis is what I'm going to try to accomplish here. But the primary mechanism that you use to achieve homeostasis is called negative feedback. And I know you've probably learned this before, most of you guys, but you need to really understand it and be able to apply it this time. So what we are going to do with negative feedback is we're going to say, okay, the purpose of negative feedback is if you're following any variable, blood pressure, calcium concentration, glucose concentration, body temperature, doesn't matter, right? The purpose of negative feedback is if we're heading for homeostasis, if the variables goes up, what should I do? Bring it back down. And if it goes down, I should bring it back up. Yes? Okay. So that means that you need to dump prior associations of the word negative, right? Because is that bad? No, that's not what negative means in that context, right? And does it always go down, as in negative means lower? No. So what does it mean in this context? It means opposition or negation. Whatever you do, I'm going to oppose it to bring you back into homeostasis. Does that make sense? So that's what negative feedback. So, and we'll come back to the set point or range idea in just a second. But let's just look at a graph of what negative feedback might look like. And when you're in lab with Joe or somebody else, you're going to do a hell of a lot of graphs that look like negative feedback. Okay. So generally speaking, phys graphs, the vast majority of them, what we look at is a variable over time, right? Okay, and so this time we're going to use an easy one that you're really familiar with, which is like body temperature. Okay, and in order to get an idea of this person's body temperature, I might only need 24 hours, right, to see the variability in the body temperature. Would I be more certain if I collected more data, 48 hours, 72 hours, right? Okay, good. So you just have a better indication, right? Now, if the variable were not body temperature and it were estrogen concentration, would 24 hours be the time scale that I wanted to look at? No. You'd need 28 or more days to look at estrogen concentration. So while time is the usual x-axis, it's not always the same, right? It's not always the same time period. Does that make sense to you guys? Okay. So it can be longer or shorter. But generally speaking, body temperature varies over the course of a day, okay? So let's look at what a body temperature would vary over the course of a day in this person who's going to have an ideal day in which they accomplish every damn thing that they set out to accomplish. I haven't had one of those in recent memory, meaning you walked your dog twice because you said you would, fed your kids 3 freaking home-cooked meals, right? You worked out, you had sex, you like read a book. I don't even know how people have those lives. But I'm going to pretend that it's possible, and we're going to accomplish this over the course of a day, and you guys are going to predict for me. So this person, who would never be friends with me, by the way, right? We would have nothing in common. Too much got your shit together. Don't even have anything to talk about. Okay, make me feel bad about myself too. All right, so getting out of bed, 6:45 in the morning, right? Because they're going to go work out before work. Are any of you those kinds of people? Yeah. I admire you, and we have nothing in common. Okay, so work out before work. So body temperature before you get out of bed, what do you predict? Low, high? Yeah, relatively low, right? And then you get up, okay? And your body temperature starts going up, not just because you're wiggling, but also there's some hormones involved, which we'll talk about later. Okay, so your body temperature goes up, and then you make a nice breakfast for your kids, right? And then you sit back down for just a second because you made so many pancakes that they're going to be busy, right? And you sit back down, you like read a book or an article, right? And then you take your kids to school, right? You come back home, you have a quickie with your husband.
That's as high as the body temperature is going on?
What?
That's as high as the body temperature is going on?
It was only like 4.5 minutes, right? He had to go to work. We're going to do it right later. This was a bonus. It was the middle of summer and I was cooking pancakes, people. All right, so the body temperature, all right. Body temperature goes up. Okay, and then you go work out. Right? And then you drive to work and you have to commute, and then if you're, let's say you're a teacher, I get really hot when I teach, do you? Yeah, and my body temperature and my heart rate goes way up too. Teach 2 classes, have some lunch, chill out in your office for a minute, close the door so nobody knows when you're in there. Right? Go pick up your kids, come home, walk the dog. Oh, I was supposed to do it twice. I did it over there. You just didn't see it. Walk the dog, watch Game of Thrones, but you don't really care about it that much. Have sex. It was morning. I hadn't even brushed my teeth yet. Give me a break, man. Quickie. Okay, so what we're going to see here is that we're looking at a graph of body temperature over time, and I tell you that the range for healthy human body temperature is like this. Okay, here's my question. Am I in a disease state right here? No. Okay, but I did go out of the homeostatic range. What would need to happen in order for that to be a disease state? Stay out, yes. So we always leave the homeostatic range. What indicates health is not that you stay in, right, but that you quickly come back in after you leave, yes? So your heart rate, your body temperature, your everything will go out of homeostatic range, and the healthier you are, the quicker you bring it back in. So some of you guys who are in your 20s, maybe teens, early 30s, if you are in good shape, because it doesn't necessarily mean you're healthy, but if you're young and also healthy, when your body temperature goes out of range, you bring it back in really quickly. Now, at the ends of your life, when you're like 4 or 85, body temperature, when it goes out, so let's talk about a fever. Fever in a 25-year-old, a fever in a 4-year-old, a fever in an 85-year-old, okay? So it's 104, which is problematic for anyone, right? That 25-year-old, is there any possibility that that person could just battle through it? Totally, right? And you might, because you're like too lazy and there ain't no ibuprofen in your house because your mama don't live there, right? And you got shit to do, right? I don't want to go, and ain't nobody love me well enough to get me some ibuprofen. So you just battle it through. But your 4-year-old, how many of you guys are parents? Okay, you let a 4-year-old have 104 temperature for any length of time? No, you don't. They can't really manage it. It's very difficult for them to bring it back in, right? How about an 85-year-old? Any of you guys deal with elderly people? Those temperatures generally require intervention, right? Really low, really high. During the middle of your life, though, you're really good as if it pops out, you bring it back in. It pops out, you bring it back in. What's the problem with staying out of homeostatic range for any length of time, for like longer times? Any problem? Below death, yeah, death is a possibility, but you actually accumulate damage, right? Just higher temperatures, more protein denaturation, right? Lower temperatures, less protein synthesis, for instance, right? So, and those things tend to accumulate over time, and that's a large part of what aging actually is. It's just staying out and then accumulating the damage over time. Okay, so what a graph of negative feedback tends to look like is that there's a healthy range, and you pop in and out of it, right? But you can see over time what the healthy range is, right? You can kind of see where it starts to correct. And so let me ask you a question. It's obvious that this part is negative feedback, but is this part also negative feedback? Right. So it's not just the bringing it down, it's the bringing it back up, right? So those are both negative feedback situations. So just one more thing about a graph before you leave this, because you're going to run into it in lab a lot and also in the lecture text. So the way that this graph is set up, time is the dependent axis, is our x-axis, and body temperature is the y-axis or the independent axis. X, what?
X, so your independent is X.
Oh, I'm sorry. Did I say this is independent, this is dependent. Sorry, I was testing you. Only two tests. Okay, independent, dependent. She's right. So here's what this graph, the way that it's set up, here's what it says. It says body temperature varies over time, which is true, right? What would the graph say if I flip the axes? Time would depend on your body temperature, which is the lamest superpower ever. And doesn't even matter, right? It's just be like, that's totally lame. So you have to set these up right because they mean something totally different if you set them up wrong, right? So you're communicating something that you didn't intend to communicate and isn't actually true. Okay, so now what we're going to do is we're going to meet the concept of a reflex arc. So we've got two topics, and I want you to relate these two before I throw in the third one. What is the relationship? I promise I'm generous and kind when you are brave in class enough to speak up. What is the relationship between the term homeostasis and the term negative feedback? Can you put those two into a statement? Go ahead.
So homeostasis is what the body needs to be able to be maintained to be able to function. Negative feedback is what keeps it in homeostasis.
Okay, I like that one. Do you have one?
Negative feedback is the, oh my god,
No, you're fine.
Negative feedback is the opposition to external forces that brings you into homeostasis.
Got it. So those two are related, right? So negative feedback is kind of the mechanism, and homeostasis is the goal, right? But now we're going to throw in a third term that's also related to these two, and this third term is reflex arc, okay? And a reflex arc is something you really need to understand, so we're going to do some think, pair, share in just a second. So let me define some terms for you. So you can't accomplish homeostasis via negative feedback if you're not, listen, monitoring the variable and correcting, right? So this is not going to happen with body temperature if nothing is checking your body temperature and knowing when to oppose it, bring it down, or bring it back up, right? So there must be portions of the body that are involved for a variable, right, with monitoring and correcting whatever that variable is. Those portions are called the reflex arc, okay? And the reflex arc, what it's going to do, it's going to sense and respond to changes primarily in the extracellular fluid, right? That's what we're going to do. So let me give you a metaphor in your home, and then we'll talk about the human body. In your home, you would like to maintain homeostasis of temperature, right? Okay. And if you have central heat and air, then how that's going to go is you set it via a thermostat. So I want to sort of look at the portions of the reflex arc there, okay? So we're going to start with that metaphor, and we're going to say, okay, the components of a reflex arc. The thing that you are measuring and correcting is considered the stimulus, or sometimes the variable, and we're going to do room temperature or home temperature, okay? So that's what we are going to do, and we're going to use our home as the metaphor. So it's a detectable change in an external environment. You have to be able to measure it, or else you couldn't correct it, right? Okay? Detectable change in the external environment, like a high room temperature. And for those of us who are parents, we know that your children, their goal in life is to leave the doors open all the damn time, no matter what. Because, yes, you sound like your mother when you say, do you think we're made of money? Right? And you literally never thought you were ever going to say that. And now I hear my husband saying it all the time. Like, it's literally the only thing that makes him lose his marbles with the kids is leaving the damn door open. And the kids are like, close the door, making fun of dad, close the door. So anyway, so the stimulus is the detectable change in the internal or external environment, the high room temperature. But now we have to have something that can detect that variable, okay? In you, it's called a sensory receptor for whatever the variable is. In your home, do you have any idea what can detect a change in temperature? What is it? It's the portion of the thermostat. It's not the whole thermostat. It's the measuring portion, the thermometer portion of the thermostat, right? And that just measures what is, yes? right? So you set it at 72, it says it's 76, right? Because your kids left the door open, right? So that's but you haven't corrected anything yet, have you, right? So that's the sensory receptor. But then what we have to do is we have to take that information that we just measured, and we have to send it to the place that knows what to do about it. Yes? We have to do that via what we call the afferent pathway. Afferent pathway, you with me? And you learned the word afferent or afferent, which is how I pronounce it so you can hear the difference. It's actually afferent and efferent, but I twang it up and say afferent and efferent. So afferent pathway is the pathway that you send it along to the place that knows what to do about it. And so, of course, in your thermostat, it's just a little electrical wire that sends the measured variable to the actual desired variable. And you're going to send it, if it were in the body, it would primarily be the nervous system, endocrine system, and also some chemicals in your bloodstream that you would use to send the message. Here it's just wiring. Okay, and then you're going to send it to the place that we call the integration center. And the integration center is the smartest part of this. It is the part that knows what the ideal setting for that variable is. You set it at 72. It can compare the measured and the ideal and decide whether the error signal between them is big enough to do anything about it. So let's think about this. If you've been in a home, and if you pay your own bills, I know that you know that if the temperature goes up to, for instance, if it's set to 72 and it goes up to 72.4, do you think the air conditioner will come on? No, it won't. And why not? Why not? Because it's super expensive if it's really inefficient. So although you haven't thought about it, your thermostat is actually set with an acceptable range, even though you told it a point, right? It's got an acceptable range. So will it come on if the temperature goes up to 76? Yeah, it will come on if the temperature goes up to 76. And you might not know what the range is, but it's set in there, right? So compares the actual to the ideal, and let's say it's 76, not 72.4, right? That much difference. Then it will do something about it, right? Doesn't always need to do anything about it, but it should measure it all the damn time. Why should it always do the first portion, stimulus, sensory receptor, afferent pathway, and integration center? Why should you always do those even if you don't need to do the other part? Because it changes, yes, right? And it could, if you only measured it every 30 minutes, right? It could go from 72 to 87, right? And then it's way harder to fix, right? And more expensive to fix, more likely to cause damage, right? And definitely your parents are going to be pissed off. Okay, so goes to the integration center, right? And the integration center is actually which portion? It's the thermostat portion, right? It's the brain of the thermostat. What?
Is that the hypothalamus?
Yeah, it's the hypothalamus for temperature, exactly. It's going to be the hypothalamus for temperature. So now here's what we do on the other part. So we decided a change needs to be made, but we haven't made it yet. So now we send a signal out the efferent pathway, or the output pathway, which again is quite often the nervous and endocrine system, but not always, right? You're going to send a signal to any organ that can effect the change that you want, and you call those effector organs, okay? So in the home metaphor, okay, what's the effector organ? 72, 76, what is it? It's 76 degrees. You told it to be 72. You're going to send out a signal that can effect that change. It's the air conditioner. Yes? Air conditioner. Or some people have swamp coolers. I don't even know how you live like that. So I didn't even know those things existed before I got to Utah, because they don't have those in Texas. Okay. They're terrible. Our neighbor right next to us lives in like an $850,000 house, and he has a swamp cooler. And I'm like, you've seen air conditioners, right? I don't even know. So sends it out to the effector organ, right? And the effector organ affects the change. It changes the variable, right? But here's the important part for you guys to understand. The response is that the variable is going to change in the direction that you want it, but here's why it has to be an arc. So all of this has to complete the circle, because you just made the response and you dropped the temperature, yes? But now what do you need to do? You need to send this response back as the new stimulus to the receptor. Otherwise, what would happen? It's just going to continue to go and go and go and go. Does that make sense to you? So it has to be an arc, and you have to close the loop every single time. Otherwise, you created the opposite problem of the one that you had, right? Okay, so one last question, and then you guys are going to do the first thing, pair share part. Okay, so the last question is, how can you relate reflex arc, now we've got a new term, negative feedback and homeostasis. Can you do a sentence or two that relates those three? Because they're related, right? But they're not identical. So how do you relate reflex arc, negative feedback, and homeostasis? Go ahead.
Reflex arc is the parts of our body performing the negative feedback to perform our goal.
Which is homeostasis, exactly. So the reflex arc is the parts, the negative feedback is the mechanism, and homeostasis is the goal, right? Does that make sense? Okay. And so homeostasis is going to be a really consistent goal almost all the damn time. Negative feedback is going to be a really consistent mechanism, and the reflex arc's parts will change different variables, right? Wouldn't you use entirely different portions if you were trying to, for instance, regulate blood glucose concentration than you would with body temperature? Does that make sense? Okay, so I'm going to throw a question at you, and here's how Think, Pair, Share works, okay? So just listen. Think, Pair, Share is done on Top Hat, so get Top Hat ready, and you're going to do the same question twice. The first time you do the question, you're going to do it alone. You get credit for participation, yes? You don't have to get it right, okay? The second time we do it, I will have explained it even more deeply, and you will have been thinking about the question the whole time. The second time you do it, you pair up with someone, and you describe your logic, change your answer if you want to, and then you answer it again, and then we talk about it. Does that make sense? Okay, so it helps to make sure that you really get concepts before you leave the concepts. All right, you ready? Give me just a second to get Top Hat going. I had to shut it down last time because it was misbehaving. And this one's a relatively easy one. They get harder as the semester goes on. I don't need you to have the hardest question first day of class, all right? Ready? Okay. Go ahead. There are 3 of you left. Make sure you click in. You can't get it wrong, but if you don't answer it, you don't get credit. I mean, you can get it wrong, but it won't count against you. 2 more people. 1 more person.
It's me. I'm just waiting for it to come up.
Oh, okay.
I got it. I've got my answer as soon as it. Or you can skip me.
Yeah, it won't make any difference, and I can. Okay. What's it doing? Why is it doing that, AJ?
I closed it all down. You're using it. I'm sorry.
You in there? No. Okay. All right, so we'll come back to that question again in just a second. The next time, your goal will not just be to get it correct, but to be able to verbalize it to another person, verbalize your logic, okay? All right, so let us now keep the whole reflex arc in our head as we talk through some examples and add one more extra little thing to it. So the next thing I want to talk about is the concept of a feed-forward mechanism. Okay, immediately that sounds like the opposite of negative feedback because it's feed forward, but I want you to understand that it's not the opposite. What it is getting a jump on negative feedback. So let me give you some examples. Okay, so some of you guys are super duper regular about your physiology. Like you have certain times of the day in which you always do something. Is anybody one of those people that always goes to bed at the same time, always wakes up at the same time, you generally eat at the same time, you probably poop at the same time every day, just everything's super regular, right? And when that occurs, your subconscious, your body, your nervous system actually learns the pattern, and it decides it's going to try to help you with the pattern so that you spend less time like trying to move from one to the next so that you can get really quickly back once you go out of homeostasis. So for instance, if she wakes up at the same time every day and she wakes up at 6:45 every day, what's going to happen if she forgets to set her alarm? She's going to wake up at 6:45, right? And generally speaking, usually slightly before that, because your body goes, I know you have things to do at 6:45, so how about I wake you up at 6:37? And I'm trying to help because I think it's going to be more efficient, right, for you to have your metabolism higher when you're actually needing to do things. And if your body is right most of the time, it continues to do that for you. It continues to say, here's my anticipatory homeostasis. Here's my prediction about what would be helpful in that situation. And if it's right, 80-ish% of the time, it's actually different for different people, but a decent percentage of the time, then that's worth the investment, right? Because it saves you a little time, saves you a little money, potentially saves you some damage from not being out of homeostasis for a long time, okay? What's going to happen to her when she goes on vacation, though? When are you going to wake up? Yep, you do. You wake up at the same time. That's my whole reason for being a crap show of a human. No, I want to make sure that I can sleep in on vacation. No, that's not my reason. It's just me. So this is called anticipatory homeostasis, or a feed-forward mechanism. And what it's really doing, guys, is it's increasing the speed of your homeostatic responses based on prior patterns, right? It's predictive, right? And so it's really used in conjunction with negative feedback systems. So why don't I have it? Because it's not helpful for me, right? It is not a cost savings, right, for me, because I go to bed at a different time every night. I wake up at a different time every day, right? And so there's no point in trying to invest in that way. But if you're really, really regular, you'll get the benefit of this kind of thing. So my pattern is so weird that my body's like, I don't know, you do you, whatever. Maybe you'll wake up, maybe you never will. So it's used in conjunction with negative feedback systems. It's getting a jump on or anticipating a needed body change. If you get really regular, then it's really helpful. And if you're not, then it's really not. If, for instance, you walk into your grandma's house and you smell chocolate chip cookies, right? You're going to have an anticipatory homeostasis response, especially if you've had that experience in her house before, right? And so you're going to begin to salivate because you smell this and it says, okay, I'm going to start to need to break down carbohydrates, right? So you're going to begin to salivate. However, if your grandma every damn time since you were an infant slapped you on the hand and said, no, those are for Relief Society, would you have the same degree of response? You would not, right? Eventually you could actually quell the response if the pattern was not dependable at all. You might not be able to completely get rid of it, but you would definitely change the magnitude of the response. Same thing with sexuality. This is almost all women, so it doesn't work very well in this class. But let's say that your partner, maybe male partner, maybe not, whatever, every single time you parade around in your lingerie, right? He has an anticipatory homeostasis response because sexuality is generally in the future. But if every single time that did not follow, do you think that that response would be as dependable over time? It would not. So if the pattern is broken for long periods of time, then the anticipatory or feed-forward mechanism can also break. Does that make sense? So this is not the opposite of negative feedback. This is predictive negative feedback, really. Okay, so now let's talk about the types of negative feedback. Okay, so we're still on the concept of negative feedback. We're still thinking about reflex arcs, but I want to give you some specific examples of reflex arcs. There are two different types of negative feedback just generally. I'm going to tell you the two names and then you match the one with what it goes with, okay? There is extrinsic regulation and intrinsic regulation. One of them is I have a problem in a body system and I handle it in-house. Which one do you think that is? Intrinsic regulation. The other one is I have a problem with a body system and I can't manage it without calling a friend. The friend is usually the nervous or endocrine system. So that one is extrinsic. Okay, so let's do some extrinsic examples, and then we'll do some intrinsic examples, and then you guys will, actually, we'll probably just do extrinsic and then the think, pair, share. But, okay, so let's talk about extrinsic example. It's generally going to be longer distance communication because hormones have to go through the bloodstream or the nervous system has to communicate long distance. But let's just create a problem with one system that can't be solved with that system. So, usually your two biggest helpers are nervous and endocrine system. And what they are doing is they're adjusting the activities of another body system. And generally, the goal is to maintain homeostasis. So let's disturb homeostasis with a specific variable. I'm going to, instead of disturbing body temperature this time, I'm going to disturb your glucose concentration. Yeah? Okay, so I have a 13-year-old. If he got 6 Butterfingers in his Halloween bag, how many do you think he would eat? He would eat 6 Butterfingers because you were 13 and you can totally manage. And he is not a diabetic, so will he live through that? He totally will, and this is how, okay? So you eat 6 Butterfingers, and it was a digestive system that caused the disturbance of glucose. You with me? Can you poop it out fast enough to change your glucose concentration? No, you cannot, right? And you already absorbed it anyway. So you're going to have to call on another body system to help with the variable that you disturbed. So the high glucose concentration, massively high glucose concentration, is the disturbance of homeostasis. That's the variable that you're going to try to fix, okay? And what is going to happen is you're going to have that massive increase in glucose, right, which is going to go through the bloodstream, and it's going to be measured by the pancreas. So in this particular instance, the pancreas is serving right now as what? It is going to measure the glucose concentration and respond to it like a receptor. Yeah, so in this particular instance, the pancreas actually serves as the sensory receptor, but it's not just the sensory receptor because the pancreas also compares your actual glucose to your ideal glucose and decides if the error message is too big. So in that instance, the pancreas is also serving as the what? Integration center, right? It's serving as both, right? Kind of like your thermostat did, right? That makes sense? Okay. So it's serving as the integration center. So here's what has happened. You ate a whole bunch, your glucose got disturbed. You detected it at the pancreas. You compared actual with ideal, and you said, too big an error message, right? But you haven't fixed it yet, yes? Right? So now what I'm going to have to do is I am actually going to have to do the output pathway. And the output pathway is going to be releasing insulin from the pancreas into the bloodstream. Yeah? Do you guys have any idea what insulin does with glucose? Some people know, some people don't. No, it doesn't break it down. Anybody know? Okay, so insulin is released from the pancreas, and what it actually does is, the problem is really that you've got too much glucose in your blood plasma. Are you with me so far? Right? It's in your blood plasma, because that's where it went when you absorbed it. Okay? So what insulin does is it allows all the cells to take the glucose from the extracellular fluid to the intracellular fluid so that they can use it for what? What do you use glucose for? Cellular respiration, exactly. And that will both supply the cells and fix the glucose level, right? So what it does is it allows cells to take in glucose, right? So more insulin is released, and it allows the excess glucose to enter the cells, which of course drops the blood glucose level, which is what I was trying to accomplish, right? Okay, but how do I complete this story? I've solved the problem, but I will create another one unless I do what? Unless the new glucose level feeds right back into the system. Where should I send it again? I mean, it's going to go there anyway, but where do I detect the new glucose level? Pancreas again. And this time it does the same comparison, right? It compares actual with ideal, only this time the error message is small, right? So it says you can stop. You can stop secreting glucose, right? So that completes the loop. Does that make sense? And the insulin secretion stops. So it's actually a reflex arc. It has to go all the way around. Everybody cool with that? Okay. So this is an example. So 2 questions for you. Do you see that this is negative feedback? And why? Why is it negative feedback? Go ahead. Exactly. And it's going out of homeostasis and you're bringing it back into homeostasis. And so one other question. Yes, this is an example of negative feedback, but why is it extrinsic regulation?
Because I have to use another system.
because it uses another body system, right? Not the system that created the problem, okay? So let's just do the opposite example, just to make sure that you guys do not think that negative feedback always brings variables down, because it doesn't, right? So let's do the opposite example. The opposite example, fasting will also disturb your blood glucose concentration, correct? Okay, so I don't care why you fast, whether it's for cultural or religious reasons, or whether your doctor told you you had an appointment at 11, doesn't get there until 12:30, and you haven't eaten since 8 the last night, and you want to eat him when he comes in, or her. Okay, so fasting is a disturbance that was created by your digestive system, or because your brain just decided that it wasn't going to eat, whatever the hell reason, okay? But either way, it's going to cause a low blood plasma glucose. And that's going to be detected by the same sensory receptors, right? But it's not going to have the same response, because that sure as hell wouldn't help, right? So the low blood plasma glucose is detected by the pancreas. That's a disturbance of homeostasis. And so what is the pancreas going to do? It's going to say, okay, I'm going to compare actual with ideal, right? I'm going to say error message, but this time the error message is in the other direction. So it's going to have a different efferent pathway or output pathway, because the other one wouldn't help, and probably a different effector, right? Instead of having all the cells, right? So let's think about what's going to happen here. So what's going to happen is I measured actual and ideal, and I did not release insulin because that wouldn't help. Instead, I am going to release glucagon. It's a different hormone. You may have never met it before, but it's easy to remember what it does, because you need glucagon when your glucose is gone. It's the one that helps you get through between meals, right? When your blood glucose drops. Okay, so I'm going to release glucagon, and glucagon is going to go through the bloodstream and go to the place in the body that I store the most glucose. And where's that? The liver, yeah? The liver stores the most glucose. And what's it going to do? The liver, in this instance, is what part of the reflex arc? It's the effector organ, right? It's the one that can effect the change, yes? It's the effector organ here. So I'm going to go to the liver, which is the effector organ, and the liver is going to release stored glucose into the bloodstream, right? And what that's going to do is, of course, raise the glucose level, okay? Good. And then what do you have to do? You have to feed that new glucose level back into the system to know when to stop releasing glucagon, or else you're going to create another problem. Does that make sense? Okay, so let's ask the same two questions just to make sure that you understand that it's never negative feedback just because it goes down, because it's this negative feedback. It totally is, but which direction did the variable go? Up, right? So it's the opposition to a disturbance in homeostasis that makes it negative feedback, not the direction, right? And then, of course, one more question. One last question, and that is this extrinsic regulation, and why? Is this extrinsic regulation, and why? Why? Yeah, because I created a problem and I solved it with another system, right? That makes sense? Okay, so with that in mind, I hope you have a good idea of reflex arcs, because I want you to talk through with at least one other person the same question, and I want to see how well you guys do on it. We're going to answer. We'll see how the class does. It never shows your answer, so don't feel like this is a shaming situation. And then I will make sure that I talk through it, or help you guys talk through it to make sure you've got it. Cool? All right, so we're going to start one more time. All right, oops. Hold on just a second. I gotta just wait right there. Think about your balls. I knew that was going to happen. This whole classroom is a hard situation for me. Okay.
Small.
It's so small. Yeah, I'm not used to it at all.